Hello world, this is Code with Fred. Welcome to a beginner's guide on the system design series. In case you want to upskill, advance in your career, learn how to solve complex problems in software development, or prepare for technical interviews. So what is system design? System design is a major phase in software development where we define the actual elements that make up a system, things like the architecture, different modules, interfaces, down to where data is going to get stored based on the gathered system requirements. In the last 2 decades, there has been a lot of advancement in how we build large-scale distributed systems. These advancements have redefined how we build software. Softwares that we use every day, like Facebook, Gmail, WhatsApp, Instagram, YouTube, and so forth, are highly available distributed systems that can handle billions of requests without breaking a sweat. Learning system design will equip you with the knowledge that you require to build systems that are resilient, systems that are scalable, available, reliable, and efficient. So your task as a developer is to understand the basic concepts of system design and apply them in real-world software solutions. Before we learn the components that make up this large-scale distributed system, it's important for us to know the system design performance metrics, and we're going to go through scalability, availability, reliability, and efficiency. Scalability describes your system elasticity. So what happens whenever there's a surge in traffic from your users? Your servers should be powerful enough to withstand the surge without compromising your system performance. There are two ways on which you can scale your applications, either vertically or horizontally. Horizontal scaling, which is also known as scaling outwards, is when you add additional servers to your existing resource pool. This is similar to delegating a task to more than one employee instead of one. So what is the advantages of horizontal scaling? Number one, you eliminate a single point of failure. Having more than one server, when one server crashes, the traffic can be routed to the other servers. So you eliminate a single point of failure. Number two, your application is going to experience fewer periods of downtimes. Since you are adding more machines to an existing pool, you don't need to switch off the old one when scaling. Therefore, the downtime is almost non-existent. Your application also has an increased system performance since horizontal scaling provides additional endpoints for client connections, which distributes the load across all the nodes. Therefore, you increase the system performance. So what are the disadvantages of horizontal scaling? Number one, there is increased complexity. Multiple servers are harder to maintain instead of one. You'll need to configure a load balancer to distribute the traffic, ensure that the nodes are communicate and synchronize effectively. Number two, it's expensive since you need to buy additional hardware. You need to configure, you need to maintain. Therefore, it's expensive compared to vertical scaling. Vertical scaling means adding additional resources to your server, such as upgrading your CPU, your memory, your storage, and network speeds. So, what are the advantages of vertical scaling? Number one, it's cost effective. The cost of upgrading a current server is cheaper compared to purchasing and maintaining additional servers. And it's also very simple because everything runs on a single machine. So what are the disadvantages of vertical scaling? Number one, you introduce a single point of failure. So what happens when that service is unavailable or when it crashes? Your application is going to be unavailable. You have a high possibility of downtimes when you are maintaining your server, and also you have hardware limitations since every hardware has a threshold for memory storage and processing power. There's a limit on how much you can upgrade a machine. System reliability is the probability that a system will perform correctly during a specific time duration. A system is said to be reliable when it adequately follows the defined performance specification and no repair is required during that period. Hardware depreciates with time, which has an effect on system reliability. but it is difficult to measure software reliability because the responses can take a longer time but still be accurate. What are the key characteristics of a reliable system? Number one, it should be fault tolerant, which basically means that it should continue working even if hardware or software component fails. It should be redundant. When a component fails, this should be replaced immediately with a components that is healthy. And it should also be resilient, which will eliminate all the single points of failure. Take, for example, a large marketplace like Amazon, where the primary requirement is that a transaction should never be cancelled due to failure of the node running the transaction. For example, a user can add an item to the shopping cart and proceeds to payment. The system is expected not to lose it even if the server carrying the transaction fails. A reliable system should be fault tolerant, that is, detect failures and migrate the transaction task to another redundant server for completion. A resilient system should be able to eliminate every single point of failure. A common way of measuring reliability is by using mean time between failures. Mean time between failure is the average time between system breakdowns, which measures the performance of a system. Take this example where a system runs for 100 hours but breakdowns on the 25th hour, and it takes 3 hours to repair the system. It it's then available for the next 22 hours and but breaks down, and it takes 4 hours to repair the system again, and then it runs for 46 hours without requiring any repair. So mean time between failures is the total operational time minus the downtime divided by the number of breakdown, which gives 46.5 hours. System availability is the probability that a system works properly when it's requested for use. It means that the system is available for use as a percentage of scheduled uptime and not due to problems or other interruptions that are not scheduled. It measures a system that has not failed or undergoing repair when it needs to be used. So how do we calculate system availability? Let's assume that the scheduled uptime is 24 hours, but the system is unavailable for 1 hour. So we can calculate availability by the scheduled uptime minus the downtime divided by the scheduled uptime times 100, which gives 95.83%. This might seem like a high score, but in systems, 95.83% availability is not good as shown in this table. A 90% availability equates to 6 minutes per hour. This might seem like a decent availability, but it accumulates to 36.5 days per year. A 95% availability equates to 3 minutes per hour, which accumulates to 18.25 days per year. An online marketplace like Amazon will lose billions of dollars every year, even with an availability of 95%. Cloud computing services like Azure, AWS, and Google Cloud has a service level agreements to commit to system reliability and availability, which is the five nines, that is 99.99%. So what's the difference between reliability and availability? Availability measures the percentage of time the system is operational, and reliability measures how long a system will function without failure. A system can be highly available but not reliable. The last metric that is used to measure the performance of a system is system efficiency. System efficiency measures how well a system works. The two metrics that are used to measure system efficiency are latency and throughput. Throughput refers to how much data can be processed within a specific period of time, and it's measured by megabits per second. There are two types of throughputs: client throughput and server throughput. Client throughput is the amount of responses a client can get per time, and server throughput is the amount of requests a server can process per unit time. Latency is a measure of delay, which is measured by milliseconds. There are two types of latency: network latency and server latency. Network latency is the time taken for data to travel between a client and the server. whereas server latency is the time taken for the server to process and respond to a request. So why does latency and throughput matter? If the latency is high, this means that there is high delay in the responses. If the throughput is low, this means that the amount of requests processed are low. High latency and low throughput impairs the performance of a system. You can look at an example of gaming where more latency matters a lot. If the latency is high, a user will experience lagging, which will drastically impair the user experience. Another example is database queries. We can improve the server latency and throughput by using a cached memory. For example, reading 1 MB from a cache memory equals to 250 microseconds. Reading the same 1 MB from an SSD, it takes 4 times the amount of time, which is 1 millisecond. Reading 1 MB from HDD takes 20 times compared to reading 1 MB of SSD, which is 20 milliseconds. And transferring 1 MB of data from California, Netherlands takes 150 milliseconds. Let us do a quick recap. In this video, we introduce system design as a major phase in in software development, where we define the actual components that make up a system. Things like modules, the architecture, down to where data is going to get stored. We also talked about the key metrics that are used to measure the performance of a system. We talked about scalability, reliability, availability, and efficiency. In the next tutorial, we are going to talk about distributed systems and the actual components that make a systems, like proxies, load balancer, caches, and so on. Make sure you subscribe, share, and give this video a thumbs up. Happy coding.